This is our lecture for section 4.6, rank. There is no video of an actual in-class lecture for this section, so we're going to rely on this document camera version where I talk through the handout and work through the examples for you. So let's get started here. And 4.6 rank, we are starting again with an m by n matrix, so m rows, n columns as usual. And we're going to define something called the row space of A. It's a subspace of Rn spanned by the rows of A considered as elements of Rn. And our notation for that's going to be row A. So let's look at an actual example here to bring this to life a little bit. Here's a 2 by 3 matrix, so two rows, 3 columns. The rows are 216 and -150. Notice that since each row has 3 entries, we think of those as elements of R3. Now we think of them as vectors, and we're going to write them horizontally. That's really just a matter of convenience. If we wanted to be really strict about things, we might say, well, they're vectors. If we want them to be vectors, we have to write them in this way as column vectors. But what happens is if we start writing the rows as column vectors, we're going to get the rows and columns all mixed up, and it just leads to a lot of confusion. So just to keep life easier, we're going to always leave rows written in this horizontal format. So what we mean by row space is, you could think of it as, for this matrix A, as consisting of all linear combinations of the form a scalar A times 216 plus a scalar B times -150, where A and B are any real numbers. So there are some theorems here that we got to consider, and the application of the theorems is going to be really important. We'll talk through the proofs, and I think the proofs are not too hard to follow, but it's really the problems that we get to that are going to be the most important for you. So theorem 13, part 1, if two matrices are row equivalent, then their row spaces are the same, are identical, are equal. This is not true for column spaces. A couple sections ago, I think in 4.4, we saw that when you row reduce a matrix, the column space can actually change. The dimension of the column space won't change, but the column space itself will be different for a reduced matrix than for the original matrix. That is not true for row spaces. When you apply row operations, the row spaces stay the same. And so let's just think why. Suppose two matrices are row equivalent, then A and B, then B can be obtained from A by row operations. Every time you apply a row operation, you're going to obtain a new matrix whose rows are linear combinations of the preceding matrix. If you just think of what we do when we add a scalar multiple of one row to another, that's like taking a linear combination of the existing rows. So the row space at any step is contained in the row space of the preceding step. So the row space of B is contained in the row space of A. This reasoning so far doesn't tell us that they're equal. It just says that row B is a subset of row A. But now, here's how we can turn things around. Since row operations are reversible, we know that A can be obtained from B through row operations. We can go back in the other direction. So using the same kind of reasoning in the first paragraph, we can conclude that the row space of A is contained in the row space of B. Well, if row B is a subset of row A, and row A is a subset of row B, the only way that could be true is if row A and row B are actually equal to each other. And we've proved that part 1 of the theorem. So let's move on to the next page. So it's part 2 of Theorem 13. If A and B are row equivalent matrices, and if B is in row echelon form, then the non-zero rows of B form a basis for both the row space of B and the row space of A. Now why is this true? Well, if B is in row echelon form, so it doesn't have to be reduced, then the non-zero rows of B are linearly independent. No non-zero row can be a linear combination of the rows below it. Now let's just try to bring that reasoning to life a little bit here. I wrote down an example of an enormous 6x9 matrix just so that, and it's in row echelon form, not reduced. It could be reduced, but it doesn't have to be reduced. And let's just identify here the pivots. We got a pivot here, 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 and then there's a pivot in the last column. Okay, and so there's 1, 2, 3, 4, 5 pivot columns, 5 pivot rows, and so what we're saying is when a matrix is in row echelon form like this, if we remove the zero rows, so we're not going to consider the zero rows, the remaining rows, thought of as vectors, are linearly independent. And they're going to be vectors in 1, 2, 3, 4, 5, 6, 7, 8, 9, R9, right? The rows are elements of R9. Now, to see why they're independent, I could cite an earlier theorem, but I just want you to think through this example to get the gist of the idea. Start with the bottom non-zero row. So we eliminated the zero row. And certainly this bottom row that I have here is by itself is independent. It's a non-zero single vector. If I then include the bottom 2 rows, since they're not scalar multiples of each other, they got to be independent. Go up to the 3rd row from the bottom. Now here's where we got to start thinking about pivots. Why are these 3 independent? We'll take this pivot position that happens to have a 1 in it for this row. There's no way this row can be a linear combination of the 2 below it, because any linear combination of the 2 below is going to take a scalar times 0 plus a scalar times 0 to try to get that 1, and it's not going to happen. You're only going to get 0 for that position from a linear combination of the rows below. So because this 3rd row up is not a linear combination of the 2 below, these 3 have to be linearly independent. And then when I move up to the next row, by the same kind of reasoning, look at its pivot position. There's no way we can get this 4th row from the bottom as a linear combination of the 3 below it, because in that pivot position, you just have 0 entry here, 0 entry here, 0 entry here. There's no linear combination that will put a 4 in that position. And so we can work our way all the way up through, because each one of these rows will have a pivot, because only the 0 rows lack pivots, and they're at the bottom, and they've been eliminated. So these rows with pivots will all be linearly independent as vectors in R9 for this example. Since the non-zero rows are linearly independent, and also since they span row B, the 0 rows contribute nothing to the span of all the rows. Now we're back to our general argument here. They form a basis for row B because they span the row space and they're linearly independent. They also form a basis for row A because row A equals row B. We know those row spaces are the same because the matrices are related through row operations. So that's actually the proof of Theorem 13, Part 2. And we're going to move on to our exercise now, which is probably, it's definitely a test kind of question. It's like a big chapter 4 kind of result, or it's a problem that we all need to be able to do, to take any n by n matrix A and find bases for each one of these three subspaces: row A, column A, and null A. And we've actually done some of this already, right? I think we've already found bases for null and column, and now we're adding row space to the mix. So let's go through our process. So I'm not going to write out every step here, but I'll write out a few steps. We're going to start applying row operations to A. And I already have a pivot in that first position, so I'll just leave it where it is. And I'm going to go ahead and get zeros below the 1 in that first column. So I'm going to subtract 2 times row 1 from row 2, 2 times row 1 from row 3, add row 1 to row 4. And here's what I get. So first row stays the same. Then I'll have 0, 0, 1, 3, negative 2, negative 6. I'll have 0, 0, 1, 3, negative 1, negative 1. And notice in that last row, I'll just have 0, 0, 0, 0, 0, 0, 0. I get a row of zeros. So now I have a pivot here with zeros below. My next pivot is right here. I don't have zeros below, so I have to apply another row operation. So I'm not yet in echelon form. We're trying to get to row echelon form. So first row is fine. Second row is fine. And now third row, I got to subtract the second row from the third row. And I'm going to get 0, 0, 0, 0, 1, 5. And I have my row of zeros at the bottom. I'm just going to call this B. Notice that this is in row echelon form. And make this up a little bit. I have a pivot here, here, and here. Correct. Notice I ended up with 3 pivots, so this third pivot column is taken care of. I have zeros below the pivot. And now I'm ready to write down my basis for each one of these subspaces. Let's start with the basis for the column space of A. Now remember, for the column space of A, I need to identify the pivot columns. But these vectors must be columns from the original matrix A. So I identify my pivot columns, and then I go back to A and copy down the corresponding. So the first one was 1, 2, 2, negative 1. My second will be the third column, 4, 9, 9, negative 4. And I'll have a third from the fifth column, 5, 8, 9, negative 5. So those must be linearly independent because the corresponding columns of B are independent. They must span the column space because the columns of B span the column space of B. But just as a note, the column space of A here is not the same as the column space of B, but the dimension of the column space of A is equal to the dimension of the column space of B. And we can use those pivot columns as long as we go back to the original matrix A to get our basis for the column space of A. All right, now what about the basis for the row space? Here, I must use rows of B because depending on the way you applied row operations, these basis vectors could be in different positions for the rows. So I'm going to, from B, take the pivot rows, so the first, the second, the third. I'm not going to take the row zeros, and I get a basis for the row space. I'm going to write them horizontally. So I have 1, -3, 4, -2, 5, 4, and 0, 0, 1, 3, -2, -6, and a third vector, 0, 0, 0, 0, 1, 5. So those are all vectors with 6 components. Those are vectors in R6, as opposed to the column vectors, which are vectors in R4. And that's it. Once I'm in row echelon form, I just copy down the rows with pivots, and that's going to be my basis for row A. Row A is equal to row B, so that's actually a basis for row B as well as row A. And so that's why we can pull vectors from B, and we have to pull vectors from B because when your original matrix, there can be changes that you make, such as moving a row of zeros down to the bottom. Here they started at the bottom, but they might not have started at the bottom of the original matrix. So you've got to pull your basis for row A from the row echelon matrix B. And so there's our basis for row A. And now we still have to find the basis for the null space. And in order to find the basis for the null space, I want to get reduced row echelon form. Because I have to solve the homogeneous equation, right? AX equals 0. So my augmented matrix starts out looking like A 0 through row ops. We're going to get to B 0, so the same as the B matrix up above, but that's not in reduced form yet. So I'm just going to go ahead and tell you what I get here for my reduced form. The augmented matrix is going to be 1, 0, 0, 0, -3, 0, 0, 0, 0, 1, 0, 0, -14, 3, 0, 0, 0, 0, 1, 0, -37, 4, 5, 0. And augmented matrix, I'm just going to have that extra row of zeros. That stands for the zero from the homogeneous equation. So I have variables x1, x2, x3, x4, x5, x6, okay, because my original matrix A had 6 columns, right? And let's see, we now got a pivot here, here, here. So we know that x2, x4, and x6 are free variables. And x1 is going to be equal to 3x2 plus 14x4 plus 37x6. X2 is free. X3 is going to equal negative 3x4 minus 4x6. x4 is free. X5 is going to equal negative 5x6. And now what I want to do is I need to put my solution in vector form here, so I need a little bit more paper. Let's see, so my solution x is going to have the form 3x2 plus 14x4 plus 37x6, x2 minus 3x4 minus 4x6, x4 minus 5x6, and then x6. So that's going to be x2 times the column vector plus x4 times the column vector plus x6 times the column vector, right? Because those are my free variables. And can I read this off? I got 3, 1, 0, 0, 0, 3, 1, 0, 0, 0, 0. They're going to have 6 entries. X4, I get 14, 0, negative 3, 1, 0, 0. And for x6, I get 37, x2, 0, x3 is negative 4, x4 would be 0, x5 is negative 5, and x6 then would be 1. And so my basis for null A, this is going to be 6 component vectors, 3, 1, 0, 0, 0, 0, 14, 0, negative 3, 1, 0, 0, and 37, 0, negative 4, 0, negative 5, 1. So I have a 3-dimensional null space. Those have to be linearly independent. We know they span the null space. That's why they're a basis. And that's the end of that problem. So let me see here if I can write this in a way where we can just see all 3 of these at once on the screen. There was our original A. Well, I'm losing that. Well, let's bring that down. Original A, and we can see the basis for column space of A, the basis for the row space of A, and the basis for the null space. The null space, we can see, as we see, usually takes the most amount of work. Both the null space and the row space are subspaces of R6 here, and the column space is a subspace of R4. All right, let's move on. Done with that one. And I'm going to move along with the handout. That was I think our 1 in 10ths calculation for this section. But there's still a lot of really important theory here for us to talk about. Theorem 14, a very big deal in this class. It's called the rank theorem. Let A be n by n. The dimension of the row space of A is always equal to the dimension of the column space of A. And it's maybe kind of anticlimactic at this point, because it's not hard to explain why. The dimension of the column space is the number of pivot columns of A. That's the number of pivot columns in row echelon form. The dimension of the row space is the number of pivot positions in row echelon form. But the number of pivot positions in pivot columns are equal, so they're always going to come out the same. In our example that we just did, we got at least the number of vectors and the basis for column A came from the pivot column. So there was one pivot column for each pivot position. The number of vectors in the basis for row A came from each row that has a pivot position. Well, there are 3 pivot positions, so there's 1, 2, 3 rows. So 3 rows containing a pivot give us the base for row A. 3 columns containing a pivot, they're not the actual basis vectors, but they tell us where to find the basic vectors in the matrix A. So dimension of column space, dimension of row space of a matrix are always equal. That's part 1 of the rank theorem. Now, moving to the next page. So A is still n by n. The rank of the matrix is, so this is our first use of this word rank, by the way. We're defining the word rank. The rank of the matrix A is defined to be the common value of the dimension of the column space of A, dimension of the row space. I guess people couldn't make up their minds whether they wanted to call it the dimension of one or dimension of the other. Since they're equal, they made up a new word, and we call that the rank of the matrix. Okay, so again, dimension of column space, dimension of row space equals the rank of the matrix. Those two dimensions are always the same. And theorem 14, part 2, is the rank theorem. And let me get a piece of paper where I can just kind of highlight this. We're saying the rank of any matrix plus the dimension of the null space of the matrix is equal to n, where A is m by n. You're going to have to memorize this because we're going to use this quite a bit, and you'll be expected to have this memorized for an exam. Why is this true? Well, it just sort of falls out of our calculations again, because if A is m by n, the number of pivot columns in that matrix A is the dimension of the column space, which is equal to the rank. But the number of non-pivot positions, non-pivot columns, is the dimension of the null space of A. So going back to our example again, we had unfortunately there were 3 and 3. We had 3 pivot columns. That tells us the dimension of the column space. We had 3 free variable columns. That tells us the dimension of the null space. And so when you add all those up, you're always going to get the number of columns, and n is equal to the number of columns of the matrix. So rank A plus dimension of null A is n. That's the second aspect of theorem 14. a note about transpose. In fact, you can always think of the row space of a matrix. If it bothers you again looking at those row vectors, we could just have called that the column space of A transpose. And actually, the column space of A is the row space of A transpose. There's this back and forth we can do between the matrix and the transpose. So what this allows us to conclude is the rank of any matrix is equal to the rank of the transpose of that matrix. And there are lots of conclusions we can draw from this relationship, and we'll start exploring this a bit. But first, just a picture here that I want you to think about. So we want to go back to this idea of linear transformation. If A is m by n, then the association of x to A times x is a linear transformation from our n to our m, right? So here's our domain space, our n, where x lives. Here's our m space, m-dimensional space, where the product of A times x lives. That's going to be an m component column vector. So what do we know about these? Well, the row space of A is a subspace of Rn, and so is null space of A. The column space of A is a subspace of Rm. So the dimension of the row space has to be less than or equal to n, and the dimension of the column space has to be less than or equal to m. But these two dimensions are always equal. So, and they're called the rank, right? So that common value, the rank, must be less than or equal to both m in n. And maybe I could have said that in a better way. The rank has to be less than or equal to the smaller of m in n. So let's explore that now in a couple examples. There we go. So I think these examples are really, really helpful for you guys now. Suppose A is a 3 by 5 matrix. So 3 rows, 5 columns. But the picture you want to have in your mind is A defines a linear transformation from R5 to R3. We're taking vectors in R5 and associating them to R3. We know the rank of A has to be less than or equal to the smaller of these two dimensions. So rank A is less than or equal to 3. Okay. Now here's our rank formula. The rank of A plus the dimension of the null space of A is always equal to, remember, it's equal to n. So in this problem, that's equal to 5. Rank A plus the dimension of the null space of A is always equal to 5, because